Welcome to this edition of Models 2 ACE. Presenting, time series forecasting of sales, which use non-causal methods, that use historical data of sales to forecast the future values of the same variable, that is sales. With respect to forecasting of sales data, causal methods are definitely more accurate methods when compared to time series methods, as causal methods explicitly and comprehensively take into account all factors influencing demand in the industry. For example, let us assume that we are trying to forecast sales of cement in a particular region. We know, for instance, that demand for cement increases with rainfall, and so, if we have data of rainfall in the region, we can directly attribute the influence of that factor, rainfall, to the demand of cement. Further, for example, if we know that the construction sector in that regional economy is growing, or how the future interest rates, and hence demand for consumer durables, GDP, savings rate etc. can be determined, we can calculate the influence of these causal variables on the demand for cement. However, the downside of these methods is that these can be used only for long-term forecasting, because it is very time-intensive, cost-intensive, and effort-intensive to collect data on such independent variables, and these cannot be done very frequently too. We have to rely on externally sourced, usually public sources for such data, and those sources do not update the data very frequently. For example, the GDP of the construction sector in a particular state may not be updated every month. So, causal methods can be used typically only for long-term forecasts, as the cost and effort of collecting and updating data for causal variables is very high, and often data is not available for the required time periods. For short-term forecasts, we have to rely on time series forecasting methods. Causal methods use regression methods such as ordinary least squares, which will be taken up in other videos. Causal methods are useful for long-term forecasts of products in maturity phase. In this video, we will take up the following time series forecasting models: simple moving average, exponential smoothing with trend, exponential smoothing with trend, and seasonality. Note that we will use the term trend, which means upward or downward movement of data. So, when a graph rises or falls, it exhibits trend. On the other hand, seasonality refers to cyclicity. For example, in the following illustration, both graphs are trending upwards or rising with time. Let us take up a data set for this problem. We have the quarterly sales data available for a product for 4 consecutive years, and for each year, the granularity of data is at the quarterly level. So, we have sales data available for 16 quarters from the first quarter of the first year through the fourth quarter of the fourth year. We will use this data and various models to predict the sales data for the corresponding 4 quarters of the fifth year. Simple moving average. This is a model that is simple to understand. This method does not capture trends and seasonalities, and hence it can be used only in scenarios with low variability, or uncertainty, and predictable fluctuations or variabilities, such as seasonalities and trends or cycles. Also, it does not take into account the entire set of historical data for the available period. Rather, it takes data only for a finite history, or periods, in time. For example, a 3-month moving average considers historical data only for the prior 3 periods and totally discards data prior to that. Further, moving averages is informed by equal weightage to the past 3 periods, for instance, in the above example, and gives absolutely no or 0 weightage to data of prior periods, as if the past history simply did not exist for those prior periods. Lastly, since equal weightage is given to past data, any sudden changes in those periods affects the forecasted value drastically, leading to sudden jerks. Despite these reservations, if moving averages are used, then the forecasted value must be multiplied by a factor, known as uplift factor, based on expertise of domain experts. This uplift factor is expected to encompass the influence of seasonalities, seasonal promotions, cyclical factors. Please note that the uplift factor can be a scale down or downgrading factor too, for example when predicting for a period following a peak. Let us use simple moving average to generate forecasts for the dataset corresponding to the aforementioned problem. We take the seasonality cycle horizon to be 1 year and the number of periods in a cycle to be 4 quarters. Basis this, the moving average takes the finite history of the recent past 4 quarters of data, assigning equal weightages to those 4 historical data points and completely discarding any prior data points. Simple exponential smoothing. Simple exponential smoothing, on the other hand, gives some weightage to prior data and more weightage to recent data. Here, weightage factor A is a value between 0 and 1, which is the weightage given to the most recent data, and the complementary fraction, 1 minus A, determines the weightage given to the forecasted value of the prior period. So, an increase in the value of A increases the weightage given to recency of data and reduces the weightage given to historical data. Another advantage of simple exponential smoothing over moving averages is that, since some weightage is given to historical data, even if small, the effect of sudden changes in historical data gets smoothed out. Since it calculates a weighted average where the weights are exponentially distributed, there are no sudden jerks. However, the disadvantage of simple exponential smoothing is that it still does not consider trend and seasonality. Exponential smoothing with trend adds on to the previous model of simple exponential smoothing, considering trend. We already noted that trend refers to upward or downward movement of data. So, when a graph rises or falls, it exhibits trend. At the cost of repetition, note that we are at the end of period T and we want to forecast demand for the period T plus 1. Without trend, we are looking at a stable demand, let us call it level, or L. LT is the forecast of just the level component of the demand or sales for the subsequent period T plus 1, forecasted at the end of period T. LT is smoothed using weights A and 1 minus A, similar to the previous model, simple exponential smoothing. LT thus considers the entire set of all the historical incremental trend values of prior periods. Similarly, TT is the forecast of the trend component of the demand or sales for the subsequent period T+1, forecasted at the end of period T. Similarly, TT is smoothened using the exponential coefficients b and 1 minus b, similar to the previous model. To determine the values of the exponential coefficients a and b, we have to run the model over historical data and choose those values that minimize errors between forecasted and actual values during model simulation. The ideal statistic for errors is RMSE, root mean square average, as it is statistically the most robust. Most softwares can produce the minimum value of RMSE for the set of errors. Once A and B are determined, these can be fixed for considerably long periods of time. They need be changed only every quarter or every 6 months, as more data sets arrive, especially for fast-moving items. Now, we add seasonality to the previous model. We use exactly the same methods to get the forecasted value as the sum of level and trend, multiplied by the seasonality index, S. Level and trend would produce a forecast like this, as seen in the previous model. Beyond level and trend, seasonality is a known variability, which corresponds to a predictable cycle, such as a festive month. For example, an average of 20% increase during Thanksgiving Day. So, the surge would start a month before Thanksgiving Day. So, there would be a cycle spanning a quarter with sales moving up steadily from the start of the quarter. This surge would be playing out as, say for example, a 10% increase in September, the first month of the cycle, followed by a 20% increase in October, again 20% increase in November, followed by a 10% in December. So, the 20% increase in October is over and beyond the level predicted by level and trend. Let us call this 20% increase as the seasonality index. The frequency of the cycle could be daily or monthly or weekly, etc. Note that this is not an uncertain cyclicity. Here, P is the periodicity of the seasonal cycle. Looking at the forecasted value for LT plus 1, we see that we are taking a division of DT, the actual demand for period T, by ST, the seasonality index for the same period. So, this ratio essentially means that we are removing the seasonality from demand or deseasonalizing demand. After this removal of seasonality, the rest of the problem gets reduced exactly to that of the previous model, that is exponential smoothing with trend, forecasting level, and trend. Again, when taking the ratio of DT and LT, we re-seasonalize the demand. LT is the demand we expect in the absence of seasonality. Hence, dt by Lt is the magnitude of the bump up due to seasonality. Thank you for your valuable time in this video. Please subscribe to our channel for more advanced analytical models.